So for this afternoon 2 lectures, I would like to talk, as I told you, about partial regularity for Navier-Stokes. And namely, so partial, namely in 3 dimensions of space. So I will consider the Navier-Stokes equations. So dtu plus u dot gradient u minus Laplacian u plus gradient p is equal to 0. Divergence u is equal to 0. So these are the Navier-Stokes equations. In 3 dimensions, so u is their, so this describes the velocity field of a fluid, of a Newtonian fluid with viscosity 1. So u is the velocity of the fluid and is a function of x and is R3 valued. And p is the pressure with values in R. And so you have this coupling between this momentum equation and this conservation of mass equation, which gives you their incompressibility constraint. So their volume of fluid elements does not change under the evolution of the fluid. So I will mention few things along the lines, along the lectures about 2D Navier-Stokes, which is very different from 3D Navier-Stokes. And the topic we'll be interested in is regularity for this equation, but regularity not everywhere as for linear equations, but partial regularity. So it's regularity almost everywhere. So we'll see why we only get almost everywhere regularity. All right. So the kind of results we aim for. So the aim is some kind of result like this, which tells you that if u p is a sufficiently nice so I will make this very precise, but let's for the moment just say sufficiently nice. That means that I have to make sense of the solution of this system. I didn't tell you what I call a solution of this system, but in a class of solutions which are sufficiently nice, if some quantity over the space-time, so I integrate u cube plus p3 over 2 over a space-time cylinder. So namely B01 times minus 1, 0. So this is our space-time cylinder, so B01 times minus 1, 0. So if this quantity is sufficiently small, so smaller than some epsilon star, then the solution is regular in a smaller parabolic cylinder, B0 1/2 times minus 1 over 4, 0. So what I'm saying here is that I consider a solution of my equation in this bigger parabolic cylinder, which I call Q1. So I'm saying parabolic cylinder because Navier-Stokes is the parabolic equation. just nonlinear parabolic equations. So we'll always consider space-time cylinders. So if this smallest condition holds in B1 times minus 1, 0, and I call this Q1. This is a notation I will use along the whole lectures. Then the solution is regular in this small parabolic cylinder. So that is the aim of our lectures, to get such kind of results. And this is what we call, or it's one form of the Caffarelli cone and Nirenberg criteria, also called epsilon-regularity. Criteria. So, the key idea, so this morning I told you one key thing is improvement of flatness. So here the improvement of flatness is coming from the smallness condition, which tells you that the nonlinearity is small. And if the nonlinearity is small, at the limit you get the linear equation. So the improvement of regularity, improvement of flatness is coming from the linear equation at the limit. Okay, and another comment I would like to make is one thing which is fundamental here is that we are able to localize. That means here it's a local condition on the solution. So I don't know at all what's happening outside of the parabolic cylinder Q1 about the solution. I don't know anything. But the main point is, if I know something locally, then the solution is regular. So there is the issue of being able to localize. And this is not so clear for two reasons. One of them is that the solution may be rough. So not much regularity on the solution. And the other reason is that you have the pressure. And the pressure is responsible for non-local effects. So we'll see how to control this and still to get the result about the regularity. So to start with, I would like to mention a few fundamental facts about Navier-Stokes. So the first thing I would like to mention is weak solution. So a weak solution of the Navier-Stokes equation is a solution in the sense of distributions. So if I take phi C infinity compactly supported in RD, I say that UP, space-time, and it's not RD, it's R3. So R3 times R. So space times time interval, or time domain. So I say that UP is a weak solution. If you have the following equality in the sense of distributions. So I put all the derivatives on their test functions, or most of them. So I put the time derivative on the test function plus u dot gradient u times phi plus gradient u gradient phi and minus p gradient phi is equal to 0. So these brackets are in the sense of the duality pairing between the distributions and C0 infinity, and their incompressibility condition, which is u greater than phi is equal to 0. So for the moment, I'm considering everything away from boundaries, etc. So I'm just saying that this is a weak solution. So the next point I would like to stress is the difference between the evolution problem. Yeah.
This function for phi is vector, and for divergence free should be scalar, right? This function.
Yeah, I don't take it divergence free here. I mean, I keep the pressure in the.
Yeah, but phi should be vector, right?
Yeah, phi is a vector. Yeah.
And u dot grad phi, that phi should be scalar, right? The divergence condition in the sense of distribution.
So in terms of integral, it's u dot gradient phi.
Yes, that phi is scalar.
Yeah, right. Okay, sorry. Okay. Okay. Sorry. So so the first one, let's say phi 1, for the first equation I take with values in R3, and the second one I take scalar. Okay, thank you. Sorry. Okay, so the next point I would like to stress is the difference between the evolution problem and the regularity problem, so the local problem. So the evolution problem is a problem I will not talk about in these lectures, but let me just say a few words about it. So evolution problem is you consider the equation in some space-time domain, so you fix some domain omega, and you look at the cylinder omega times 0t for some time t, and you supplement, so you have the Navier-Stokes equation, and you supplement the Navier-Stokes equations with some initial, so Navier-Stokes equations, plus boundary condition, on partial omega. So for example, no slip boundary condition. And so boundary condition and initial data. So u at time 0 is equal to some u0. So here everything is deterministic. So you impose boundary condition and initial data, and you focus only on omega. In what we'll do, we will consider the regularity problem. And like in the lectures of this morning, we'll only have local, we'll only consider the solution locally. So the regularity problem is local, meaning that outside of the ball, we don't know what's happening, but we don't care about what's happening outside the ball. And we only consider the equation in some parabolic ball Q1 and want information in some smaller ball Q1/2. What's happening outside we don't know. And in some sense, so we don't have boundary conditions, neither initial data. But what in some sense, replaces initial data is the knowledge of the flow here. That means you know some history of the flow up to this time, which is time minus 1/4. So this replaces their initial data in some sense. And what replaces their boundary data is their knowledge of the solution in this ring. Okay, so this replaces, I mean, it's just a way to think about it. Replaces initial data. And in the ring, replaces boundary condition. But so this is just a way to think about it, but we will never talk about boundary condition or initial data during these lectures, because we were only considering things locally. Okay. So another fundamental fact I want to talk about is the local energy equality. So now I'm assuming that everything is smooth and I want some a priori estimate on the solution. So assume U and P are smooth. So if you know U and P are smooth, then you can test against, for example, phi times U with phi C infinity compactly supported in R3 times R with values in R. And you can do integration by parts. So this is just some local quantity, so you don't have to worry about decay at infinity because it's just localized. And if you test your Navier-Stokes equations against this test function, you get some equality, which is the following one. So for all t smaller than t prime, no, sorry, let me write it the other way. So for all t prime smaller than t, I get that the integral over R3 of u dot t square dx, so x dx, plus the this is just some simple computation starting from you write the equation, you test against u phi, and you integrate by parts. So I just give the result of the computation. So this term plus now an integral over R3 times R. An integral between t and t prime, R3, so 2 times this, gradient u, square dx ds. So this is equal, because everything is smooth, to one term which is the integral over R3 at u x t prime square phi of xt prime dx, and then plus terms which come from the nonlinear term and the pressure term. So you have, for example, integral between t prime and t integral over R3 of u squared dt phi plus Laplacian phi dx ds, and plus another term which is the integral between t prime and t integral of R over R3 of p plus, or u squared plus 2p mu dot gradient phi dx ds. So this is what I called local energy equality. And for there, so this is if everything is smooth. So for the solutions we'll deal with, there won't be as smooth as that. So we'll just have a local energy inequality. So instead of this equality, we'll get the inequality like this.
Excuse me, t prime is greater than t.
Sorry, I mixed.
Okay.
Yeah.
Okay.
Here, yeah. Yeah, thank you. Okay. And so this this is really the key thing, as was Cacciopoli in this morning's lectures. This is some kind of substitute for Cacciopoli if you want, because if you are able to control the norm of u in L3, so here you have a u square u, so u in u cube, and if you are able to control p, so you notice that, we'll come to this later again, but my assumption before was on u3 plus p 3 over 2. So if you, here I have exactly u3, and here I have a p times u. So if I have p in S3 over 2 and u in S3, then this is integrable and I can control this term. So if you can control this and p, then you can control the left-hand side. And the left-hand side gives you control about u in L infinity in time, L2 in space, and gradient u in L2, L2. So this gives you some compactness in some sense. So if you want, you can read this equality or inequality, as we'll see later, as a substitute for Cacciopoli inequality, this setting. But the most difficult thing, more difficult thing here is of course the pressure, which we didn't have this morning. Okay, so now, yeah, I want to say a few things about the pressure. So, so in essence, the proof I will show you about the compactness argument later, that they will work as the proof of this morning, in essence. But there is one really much more difficult point, which is the treatment of the pressure. And the pressure actually will make the solution not as regular in time as there are in space. So the pressure is responsible for some non-local effects. And simply from the weak formulation of the equation, you see that Laplacian P, so if I apply the divergence to the equation, you see that, and use the incompressibility, Laplacian P is equal to divergence of divergence, so of u dot gradient u, but u dot gradient u, using incompressibility, you can also write it as divergence of u tensor u. So this is something I will use quite often, going from one to the other. And so this is divergence of u tensor u. So the pressure depends in a non-local way on the velocity field. And so the regularity in space is not, in some sense, influenced by the regularity, the non-local effects. Of the pressure of P. But the regularity in time is. Is influenced and the way to see this is through an explicit example. So I will show you an example due originally to serine. And he gives the example of a velocity field, which is like A of t. So u is depending on x and t. Is equal to A of t gradient psi of x. So where A is a bounded measurable function. Let me say L infinity. And psi is any harmonic function. And you can check that this is a solution to Navier-Stokes equation with P of xt, which is A prime t times psi of x, also minus sign here, minus 1/2 of u squared. So what you see is that the irregularity in time of u, of dtu, so irregularity in time of dtu is related to the regularity in time of p. And considering this example, you can construct counterexamples later. And you also see that if you assume some integrability of the pressure in time, you will have some regularity of u in time. Namely, if you assume, for example, that P is L3 over 2, you can have that u is C1 over 3. So if P is L3 over 2, so just integrable, then u is Hölder continuous with exponent 1 over 3. We'll see that. But really, the regularity in time of dtu or of u depends on the regularity of the pressure. This is really one of the key things we'll see over again. Okay, so so the last important aspects about Navier-Stokes equations for this very introductory comments is scaling. So scaling means that if you take some scaling parameter lambda, a real number, and if you have u a solution, then u lambda, which is in variables, let's say y tau, which is defined like u lambda times u of lambda y lambda square tau, is a solution of the equation. So u solves Navier-Stokes implies that u lambda solves Navier-Stokes. So you can check this easily. So the lambda here is coming from the nonlinearity, and the lambda and lambda square here are the parabolic scaling. So this is the reason I take parabolic balls QR, which are always like B0R times so minus R square 0. And so this scaling means that if I want to talk about have a criteria which says that if something is small, then the solution is regular, for example. That means that I need to consider scale invariant quantities. If I don't consider scale invariant quantities, I could just change the parameter and make the quantity small or large as I want. So having a smallness criteria only makes sense if I consider a scale invariant quantity. So maybe I can write this like this. Oh, now I erased local energy. Oh, so anyway. So so for example, the result will read if some scale invariant quantity f of u, p, and r. So in the result I showed you before, r was taken equal to 1. But if I have some quantity which depends on r, that quantity should be invariant under the scaling. So meaning that if I have u lambda, p lambda, and r, this should be equal to or r over lambda f of u p r. So if some scale invariant quantity f u p r is small, then the solution is regular. So this is the type of result I'm aiming for, and again, I need to consider scale invariant quantities in this sense, because otherwise I could always make the quantity smaller just by scaling, which is not reasonable. Okay, so and then you so I would like to mention one key difference between d equal to 2 and d equal to 3. D equal to 2, the energy is scale invariant. So the energy, so if you consider now solutions which are on the whole of R3, so now I'm just considering their initial value problem, just as a small parenthesis. With initial data U0 in L2, divergence free. So the energy, so before I derived the local energy equality, but if you take phi equal to 1, and if your function has some integrability properties, then you can have a global energy equality. So the energy for Navier-Stokes is 1/2 of u t squared over R3 plus gradient u square over so time interval dot R3 is smaller than 1/2 of R3 U0 squared. So this you can get again from the local, same computation as local energy equality, but by taking a test function which is u instead of phi times u. And the energy in 2 dimensions is scale critical, so invariant under the scaling. Whereas in 3 dimensions, the energy is supercritical, so it's not invariant under the scaling. And actually, when you let so the energy is not controlling very well the small scales, the nonlinearity. So that's one of the big problems in 3D is that the energy does not give much information about the solution. So energy is supercritical. So that's just a small parenthesis about that this was considering initial value problem. But from now on I will talk again about the local regularity problem. So just to finish the introduction, I have to tell you now about the nice class of solutions where we are looking, where we are working. So so when I first stated their epsilon-regularity, I told you I take UP or a solution in a sufficiently nice class, and now I'm defining this nice class. So nice class of solutions which are called suitable solutions. I will write local suitable weak solutions. And I will denote this by local suitable weak solution. So a suitable solution UP is a solution so that UP is a weak solution. So in the sense of distributions, so UP is a suitable solution in Q1. So Q1 is the parabolic cylinder of size 1. So UP is a weak solution. UP satisfies some bounds. So U is in L infinity in time, L2 in space of Q1, intersected with L2 in time, H1 in space. Q1. And P is L3 over 2 in time and space of Q1. Later on I will most likely drop the T and X subscript. And moreover, U and P satisfies local energy inequality for all phi in C infinity compactly supported. So in B01 times minus 1, 0. And non-negative. Or, yeah, non-negative. So let me write it again in this case. So R3, so U dot T square phi dot T plus 2 times R3 of gradient U, so times so 0 T, I'm sorry, minus 1 T. Minus 1 T over R3 of gradient U square. This is smaller than U square. So again on minus 1 T R3 of dt phi plus Laplacian phi plus integral of this quantity, which is U square plus P plus 2P U dot gradient phi. Okay, and this for almost every T in minus 1, 0. So we always work in this Q1. So this is time 0, this is time minus 1. We always work in this Q1, and the fact that it's defined in negative time has absolutely no impact on the results, but it's just for convenience. We want to say that 0 is finite. So it's some local region in space-time. And now that I have defined the suitable solutions, I have the nice class of functions I was talking about, for which I have local energy inequality. So I can localize and get compactness properties from this bound plus their energy inequality. And from this I can state a precise result about the epsilon regularity. Are there any questions about this? Yeah?
I guess you are missing I in the second term.
Ah, yeah. Sorry. Thank you. So now I can state the precise result, and the goal will be to give a proof of it. So I call it so there are several kinds of epsilon regularity result, and this one I call it the U plus P or epsilon regularity criteria. So this is really a local terminology. But we'll see other epsilon regularity criteria like the lim sup criteria. So the U plus P criterion which I will focus on is the one I stated before. So the theorem is the following. So there exists constant epsilon star in 0 infinity C and alpha in 0, 1 such that for all local suitable weak solution UP to Navier-Stokes equations in Q1 if the integral of over Q1 of U cube plus P square over 2 is smaller than epsilon star, then U belongs to C alpha R. So Hölder continuous in time and space of Q1 half bar. So I will explain some notation about this theorem, but basically this is saying that if this quantity is sufficiently small, then the solution is regular. So the first notation I have to make precise is a notation for this space. So C alpha R in the closure of the Q1 half parabolic ball, a parabolic cylinder, means that U is in L infinity of Q1 half, and for all xt x hat t hat in Q1 half bar U xt minus U x hat t hat is smaller than the semi-norm, so U times, so T minus T hat alpha plus X minus X hat 2 alpha. So it's like Hölder continuous with exponent alpha in time and Hölder continuous with exponent 2 alpha in space. And these exponents are consistent with the parabolic scaling, of course. And the good thing is that as like this morning, we have a characterization of these functions in terms of integrals. So like the Campanato lemma I showed you this morning. And this again is a key tool to make the proofs work. So there, so the comparator tells you that U is in C alpha parabolic. Let me say it for Q1, but you have the same characterization, of course, for any parabolic ball cylinder. If and only if U is in LP of Q1, so I take P in 1 infinity. So this morning we only needed the characterization for P equal to 2. Now we'll need it for some P, especially P equal to 3 and P equal to 0.3. So if and only if it's in LP of Q1 and the sup over R bigger than 0 over all points x0 t0 in Q1 of the mean of QR, so centered at x0 t0. So this is just a parabolic cylinder now. Instead of centering at 0 as before, I center at the point x0 t0. So I consider this point, this parabolic cylinder, which is QR x0 t0. So this is of size roughly R, and this is roughly of size R squared. So I just center the parabolic ball, a parabolic cylinder at any point, and I look at the U minus the mean of U, R, P, dx dt. And now this mean here is, so the mean here is over QR. So like this morning, this is 1 over the measure of QR squared, QR, times the integral over QR. But the measure of QR is like, so I'm in 3D, so this is like R cubed times the height of the cylinder, which is like R squared. So this is like R5, okay, because of the parabolic scale. So I'm taking really cylinders which are R squared in vertical size and R radius R in horizontal size. And so one other thing before proving the theorem I want to say is so the quantity FUPR, which we are considering, so this is stated for R equal to 1. But I can state it by rescaling a similar lemma for the ball QR. So I'm considering FPUPR, which is 1 over R squared, QR of U cubed plus P square dx dt. So this gives me a quantity FUPR. And that quantity is scale invariant in the sense that I wrote before. So FUPR is equal to F of U lambda, P lambda, and R over lambda. So scale invariant in the sense that, of course, I have to change the R if I change the scale. And the theorem can be restated with the same epsilon naught as FUPR smaller than some epsilon star implies U is C alpha in the parabolic ball QR over 2 bar. Okay, so this is really what I meant with scale invariance. This quantity scale invariant, so you cannot make it small by just changing the scale. You could not have a regularity criteria just by for non-scale invariant quantities. The quantity needs to be scale invariant in that sense. Okay, and one last thing I want to mention before I start the proof is so you notice here in this theorem we have we gain Hölder continuity in space but also time, and this is related to the fact that we made an assumption on the integrability of the pressure. In the definition of local suitable weak solutions, you have an assumption on the regularity of the pressure, which is P L3/2. And since you assume this, you can gain almost C 1/3 regularity, Hölder continuity with exponent 1/3 for the velocity. All right. So okay. So are there any questions on this result? Okay, so the proof I will so there are many proofs of this result. I will tell you a bit about the history of the problem after the proof. But the proof I will show you is due to Lin. Van Merlin, who gave a proof in '98 based on this compactness argument. So okay, so let me just outline the proof first. So we consider so along the proof the goal is to estimate this kind of quantities. Okay, and again, like this morning, I will center everything at 0, and if you want the result at another point in Q1 bar, you just need to do the same procedure but centering the balls at another point. But this is just mainly technical. There is nothing fundamental. So if you understand for balls centering at 0 and shrinking to 0, you understand for everything. So I will consider the oscillation. So like this morning, we had some oscillations. So here, it will be even simpler because we're comparing to, we want Hölder continuity. So we are comparing to constant functions. This morning, we wanted to have C1 alpha regularity. So we were comparing to linearly growing functions. So now I will just compare to constant functions. And so I define the oscillation as the integral of QR of U minus UR 3 at the power 1/3. But this is not enough. So this is, at the end, I want a result about how this shrinks with R, if I want to get the epsilon regularity result. But this is not enough. At each step, I also need to keep track of pressure, because pressure is involved in this. So I also need to keep track of pressure, even if the pressure does not appear in the final result. So I will consider the mean of the pressure minus P R of T 3/2 QR 3/2, and I will put an R here. Okay, so this is the quantity we'll iterate on. So this R comes from the fact that the pressure will not be will not be, it's just L3 over 2 in time, and it will not be better. It will not be Hölder continuous. So the pressure will be, so you cannot prove something like this on the pressure. Consider this quantity under pressure. So there is an R here, and this mean here depends on time. So this is just, so if you look at the literature, sometimes it's brackets like this. So I just denote it like this with a time t, so there is no ambiguity. And this is just the mean in space. So this is just the mean over B0R of P dot at time t. Okay. So P will be Hölder continuous in space, but not in time. Okay, so that's why the quantity we have to consider for P in order to make the iterations work is different from the quantity. But basically, as I told you, pressure is making things more complicated, of course, because there are some non-local effects. But if you want to understand how things work, you can first consider this quantity as if there was no pressure in the equation. And do the whole proof. Okay, so this is the quantity we'll consider.
Definition of oscillation. Pressure is power 3 over 2, 3 over 2.
2 over 3, sorry.
2 over 3.
Thank you. Okay, so a sketch of the proof. So again, like this morning, there are two main steps. So step 1 is improvement of flatness. So for the improvement of flatness, the idea is to say that if, so let me denote the smallest condition by, let's say, S epsilon naught, or epsilon star. So if UP satisfies S epsilon star, then there exists some theta such that the oscillation of UP theta is smaller than theta 2 alpha epsilon star for some theta in 0, 1/2. So it's like this morning. You first, by contradiction, by compactness, you're converging to now the linear equation. You have some regularity for the linear equation, and that gives you an estimate at some scale theta for the nonlinear equation. And then you will iterate this estimate down to the small scales. So the step 2 is iteration of step 1. And actually, in order to make the iteration work, you need to consider, so this is mainly a technical point, you need to consider a solution to the Navier-Stokes equation with drift. So ut plus u dot gradient u plus b dot gradient u minus Laplacian u plus gradient p is equal to 0 and divergence u is equal to 0. So you have to add this drift term. And you have, of course, a similar notion of local suitable weak solution for this Navier-Stokes equation with drift. And the drift adds one term in the local energy inequality, but just think of it as if the drift was not there. So I think I will make a short break, and then we start again in 10 minutes for the proof of the proposition.